The NEC, National Electrical Code, uses a higher value for K in voltage drop calculations to account for several factors. These factors can affect the accuracy of the calculations. Firstly, variations in conductor temperature. The NEC assumes a conductor temperature of 75 degrees Celsius for voltage drop calculations. However, in practice, conductor temperatures can vary significantly. This is especially true in high current circuits or locations with poor ventilation. A higher K value compensates for these potential temperature variations. Secondly, skin effect. At higher frequencies, current tends to flow near the surface of the conductor. This increases the effective resistance. The NEC doesn't explicitly account for skin effect in its voltage drop calculations. However, using a higher value for K helps to compensate for it. Thirdly, impurities in copper. The NEC assumes that the copper used in electrical conductors is pure. However, impurities in copper can increase the resistance of the conductor. Fourthly, manufacturing tolerances. There can be some variation in the cross-sectional area of conductors which affects the resistance. By using a higher value for K, the NEC ensures that voltage drop calculations are conservative. This ensures conductors are not undersized. This practice helps to prevent overheating. It also helps prevent insulation breakdown. Finally, it helps prevent other electrical hazards. The NEC uses a conservative approach to voltage drop calculations for safety reasons. While field measurements might show lower K values in certain scenarios, relying on the NEC higher value ensures a safer and more reliable electrical system. The K factor in voltage drop calculations represents the direct current resistance of a conductor. It uses a circular millifoot at a specific temperature, typically 75 degrees Celsius per the NEC. The voltage drop formula using the K factor is voltage drop equals 2 times K times I times D divided by circular mils, where I is the current in amps, D is the one-way distance in feet, and circular mils is the cross-sectional area of the conductor. It is important to note that the factor of 2 in the formula is for single-phase 2-wire circuits or 3-phase circuits. For single-phase 3-wire circuits, the factor of 2 is not used. The K factor itself represents the resistance of a specific length and cross-sectional area of the conductor material. Using a higher K value results in a higher calculated voltage drop. This leads to the selection of a larger conductor to meet voltage drop requirements. The NEC recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. Using a higher K value ensures that these limits are not exceeded. There are many factors to consider when determining the appropriate K value for voltage drop calculation. These factors include conductor temperature, skin effect, impurities, and manufacturing tolerances. The NEC provides a conservative value for K to account for these factors. In practice, it is possible to measure voltage drop in existing circuits and calculate an effective K value. However, these measurements should be performed under normal operating conditions. They should account for variations in load and temperature. It is important to consider all relevant factors when determining the appropriate K value for voltage drop calculations. If there is any doubt, it is always best to use the conservative value provided by the NEC. The NEC doesn't explicitly list a single K value for copper. Instead, it provides guidance in Chapter 9, Table 8. This table lists the direct current resistance for various conductors. This includes copper and aluminum. The K value can be derived from this resistance value at a specific temperature. The commonly used K value of 12.9 for copper is based on this table. It assumes a conductor temperature of 75 degrees Celsius. Variations from this value arise from different assumptions about temperature, purity, and other factors. The skin effect becomes more prominent at higher frequencies. In alternating current circuits, the current density is not uniform across the conductor. Instead, it concentrates near the surface. This reduces the effective cross-sectional area of the conductor. This increases the resistance. The skin effect is more pronounced in larger conductors and at higher frequencies. The NEC doesn't provide a specific formula to account for skin effect in voltage drop calculations. However, the use of a higher K value helps to compensate for this effect. Impurities in copper, even in small amounts, can increase its resistance. The NEC assumes a certain level of purity for copper conductors. However, variations in the manufacturing process can affect the actual purity. Higher levels of impurities result in higher resistance. This increases voltage drop. Manufacturing tolerances also play a role. Conductors are manufactured to meet specific size requirements. However, there can be slight variations in the cross-sectional area. These variations affect the resistance of the conductor. The NEC accounts for these tolerances by using a conservative K value. The choice of K value can impact the overall cost of the electrical installation. Using a lower K value may allow for smaller conductors to be used. This reduces material costs. However, it is important to ensure that the voltage drop remains within acceptable limits. It is also important to consider the potential for future load growth. Using a conservative K value provides a margin of safety. This ensures that the electrical system can handle increased loads without exceeding voltage drop limits. The NEC provides a minimum standard for electrical safety. It is important to consult with a qualified electrical engineer. This ensures that the electrical system meets all applicable requirements. The engineer can perform detailed voltage drop calculations. These calculations take into account all relevant factors. The engineer can select the appropriate conductor size. This ensures that the voltage drop remains within acceptable limits. They can also verify that the electrical system meets all applicable codes and standards. The use of a spreadsheet for voltage drop calculations is a common practice. It allows for quick and easy calculations. However, it is important to ensure that the spreadsheet is accurate. It is also important to use the correct K value for the conductor material and temperature. The spreadsheet should also account for other factors. These factors include the length of the conductor, the current, and the conductor size. The results of the spreadsheet calculations should be verified. They should be compared to the NEC requirements. The NEC provides tables and examples for voltage drop calculations. These resources can be used to verify the accuracy of the spreadsheet calculations. It is important to understand the limitations of the voltage drop calculations. The calculations are based on certain assumptions. These assumptions include a constant load and a constant conductor temperature. In reality, the load and conductor temperature may vary. These variations can affect the actual voltage drop. It is important to consider these variations when interpreting the results of the voltage drop calculations. It is always best to err on the side of caution. Use a conservative K value. This ensures that the voltage drop remains within acceptable limits under all operating conditions. The NEC is updated every 3 years. It is important to stay current with the latest edition of the NEC. The NEC may include changes to the voltage drop requirements. It may also include changes to the K values for different conductor materials. The NEC is a valuable resource for electrical professionals. It provides guidance on all aspects of electrical safety. It is important to consult the NEC when designing and installing electrical systems. Using the NEC recommended K value for copper conductors ensures a safe and reliable electrical system. This accounts for various factors. These factors can affect the accuracy of voltage drop calculations. By following the NEC guidelines, electrical professionals can minimize the risk of electrical hazards. They can ensure that electrical systems operate efficiently and safely. In conclusion, while field measurements and other references might suggest lower K values for copper, the NEC higher K value serves as a conservative safeguard. It accommodates real-world variations in temperature, purity, and other factors. It leads to safer and more reliable electrical installations.